Welcome, everyone. Thank you for joining us today. My name is Natalia Martin, and I'll be your moderator for this webinar. Today, we're talking about Engineering Grade IEC 62443, a guide for power generation. Our panelist is Andrew Ginter, who is VP of Industrial Security here at Waterfall, and he'll give his perspective on IEC 62443, seen through the lens of cyber-informed engineering. Couple of notes before we start. This webinar is being recorded. An email with the link to the recording will be sent to all of you within the coming days. There will be a Q&A session at the end of the webinar. Please make sure to submit your questions in a Q&A panel at the bottom of the screen, and you can do it at any time during the session. We'll try to answer all of your questions, but in case we're out of time, which happens sometime, we'll make sure to reach out to you individually via email. And with that, Andrew, the mic is yours.
Thank you, Natalia. And thank you, everyone, for joining us. I am here on my own. We all wanted Dr. Jesus Molina to be here, but he has taken ill, unfortunately, and is under doctor's orders not to be here. So, we're all hoping he gets better soon. He is still working on a report that this webinar is sort of giving a high-level overview. He's going to dive into detail in the report. Given the circumstances, the report will probably be a couple of weeks late. But, you've all signed up for the webinar. You will get an email, hopefully from the marketing team, when the report comes out, saying here it is to download. And so with that, I'm, the research Jesus was doing and what I'm going to speak to today is using the new cyber-informed engineering way of looking at things, the engineering perspective, to augment, to make, using 62443 better. So that's my goal. Let me turn off my video so the internet can focus on getting you my voice and the screen here. And let's begin. So let's start with the 62443 family. Family of standards, there's like, do the math, there's 15 standards here. Occasionally, some of them are not standards, they are technical reports. Most of these are standards. There's only 6 or 8 of them that have been published. The remainder are still in progress. I'm going to be talking mostly about 3-2, which is risk assessment. I'm going to be talking about 3-3, which is security controls, and especially security levels, which is sort of the security target. What are we aiming for with our security controls? And on the end, I'm going to say a few words about 4-2, which is cybersecurity certifications. A couple of things to remember about the 62443 standards. Most of these are standards. And so, look at the language of the standard. The standard defines the minimum that you must do to be compliant. It says, if you want to be compliant with the standard, you must do X and you must do Y and you must do Z. This is not really a goal saying, hey, everyone, we'd like you to be here. This would be a really secure posture. It's the minimum. The second thing that you have to remember about the standards is that some of them are quite old. I mean, 3-3 to me is the brains of the whole thing. 3-3 is the security controls. It's what you have to do to secure your systems, our systems, these systems. And it's 11 years old now, and it's being updated. And the world has changed. So what used to be the minimum 10, 11 years ago is now in many circumstances seen as inadequate. And this is why the standard is being updated. So when you use these standards, bear in mind that they are the minimum that what might be reasonable for our sites, for our, reasonable protection might be more than the minimum specified in the standard. A concrete example of that is these standards are designed to be cross-industry. They apply equally to small shoe factories as they do to large power plants. And large power plants is, the focus of this presentation. These are the examples. These are the consequences that I'm going to be diving into for power plants. But the standards apply equally for small shoe factories and large power plants. And so when we read the standard, one of the reasons we have to choose security level targets is because a large power plant is going to have a very different security level target than a small shoe factory. And so if we do the minimum the standard requires for anything, we're going to be implementing a shoe factory security program for our large power plant. So this is why 3-2 exists. This is why we have to do risk assessment to figure out what parts of the standard should apply to our system. And I'm going to be, so that's 62443. Let's introduce cyber-informed engineering. This is an initiative from Idaho National Labs. The U.S. Department of Energy is paying for it. There's a strategy been published. There's an implementation guide been published. The language of the strategy and the implementation guide, I mean, these things were written by PhDs. The language is abstract. The language is, comprehensive. Informally, cyber-informed engineering is positioned as a coin with two sides. One side of the coin is cybersecurity. Teach engineers about cyber threats. Teach them about cybersecurity mitigation, cybersecurity controls that can be deployed, cybersecurity technologies and processes. The other side of the coin is engineering. What does that mean? Well, the textbook example is, let's consider a large power plant. Think old school, a coal-fired power plant. A large one, let's say 1,500 megawatts, 1.5 gigawatts. We're talking, 3 half gigawatt generators. Each generating unit is a conveyor that conveys coal powder, coal dust into, pulverized coal into a furnace, blows it into the furnace. The dust ignites almost instantly. Within a second, it's consumed, producing carbon dioxide, water, and heat, heating a massive boiler. The boiler is, 6 stories tall, 4 stories tall. These are huge devices. And imagine that every one of us is the technician responsible for these 3 boilers. We calibrate the instrumentation that is connected to measure the status of the boilers in the furnace. We replace that instrumentation when it fails. We have the gamma ray testers to test for in situ corrosion without shutting anything down. These boilers are our baby. We work 8 hours a day within the kill radius of a worst case boiler explosion. Every one of us on the call, how would we like to be protected from a cyber attack that overheats the furnace under one of our boilers? Would we prefer a mechanical valve that, an overpressure relief valve that if the steam pressure in the boiler is too high, it forces a piece of steel against a spring, the steam escapes, and there's no explosion? Or would we prefer a longer password on the PLC controlling the boiler? Most of us would prefer the mechanical valve, thank you, because it will always do its job. It's unhackable. It does not matter what kind of cyber attack is launched. There's no CPU in the mechanical valve. With a valve in place, the boiler cannot overpressurize. The truly, the gurus that I asked the question of say, Andrew, you're being deceptive here. You're asking me the wrong question. If my life depended on it, I would want a mechanical valve. I'd want 3 or 4 of them because these things do wear out. Okay, they corrode. I would want a longer password on the PLC, and I'd want a boatload, an absolute boatload of cybersecurity beside it, because this is my life on the line. And they're right. They're absolutely right. Cyber-informed engineering is positioned as a coin with 2 sides. We spend the entire coin. We don't spend one side of it or the other. We spend the entire coin. We need both engineering and cybersecurity. And here's the thing. Engineering has been neglected historically. Where is the mechanical overpressure relief valve in the NIST cybersecurity framework? It's not there. Where is it in ISO 27001? It's not there. Where is it in the industrial 62443? These are all cybersecurity standards. The overpressure relief valve is an engineering mitigation for unsafe conditions. It's never going to be in the cybersecurity standards. It is a tool that is available to manage physical risk. And it's applied routinely. These valves are installed routinely on these boilers to deal with the risk of an earthquake coming in and crimping, collapsing the outlet pipe on the boiler, trapping the steam in the boiler and causing the boiler to overpressurize. They're designed to deal with the risk of a hurricane coming in and blowing too much oxygen into the furnace and overheating the boiler and overpressurizing the boiler. They're designed to deal with physical risk to, industrial physical operation. They can also be used to address cyber risk, but they have not been used. Or rather, I've seen them used sporadically. Some people use these engineering techniques, some people don't. Cyber-informed engineering, the goal of cyber-informed engineering, one of many goals, is to use these powerful engineering tools that only exist in OT security, use these powerful tools systematically and universally, not sporadically here and there. And so, you can think of these, electromechanical safeties as engineering grade protection rather than cybersecurity. Well, if engineering grade is the overpressure valves, what's cybersecurity? It's IT grade. Well, what's the difference? Well, imagine that the engineering profession has figured out how to build suspension bridges at 1/3 of the cost of today's suspension bridges. Massive savings. How do they do this? I don't know. Use carbon fiber instead of steel or something. The problem with the new design, imagine that the problem with the new design is that it is absolutely riddled with harmonic frequencies. I mean, we all remember vaguely the Tacoma Narrows disaster of 1940. One of the world's first very large suspension bridges. The engineers of the day have not figured out harmonic frequencies. And so a stiff breeze came up, started the bridge oscillating, and it just built up until it tore itself to pieces. Imagine that the new design, carbon fiber, blah, 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 is riddled with harmonic frequencies. People walking across the bridge can start the wretched thing vibrating badly enough to eventually damage itself. And so the engineering profession has built into the bridge active dampers, vibration dampers. The hydraulics with, multiply redundant hydraulics, multiply redundant power supplies, multiply redundant control systems, so that when we walk across that bridge, it feels rock solid because all of the vibration has vanished. How happy would each of us be driving across that bridge every day if we knew that the design engineer hoped that if there was a cyber attack on the artificial intelligence controlling the bridge, controlling the dampers, hoped that we could detect the attack before the bridge tore itself to pieces? How happy would you be knowing that the design engineer hoped that if we detected the attack in time, we could scramble an incident response team fast enough to prevent the attack from crippling the AI? Hope is not what we expect of the engineering profession. When public safety is at risk, when the consequences are unacceptable, we expect designs that are going to carry, bridge designs that will carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. I asked a bridge designer who designs pedestrian bridges, I said, how do you know how much load to calculate for the bridge? He says, well, it's easy. People are mostly water, and most of them are shorter than 2 meters. So calculate the weight of 2 meters of water, the width and the length of the bridge. That's your maximum load, he says. And then he says, you multiply that load by 8 and you build the bridge to hold that load, because these are people. Failure of the bridge under load is unacceptable. We expect cyber designs, when public safety, when national security is at risk, we expect cybersecurity designs that are going to hold up reliably against a specified threat load until at least the next opportunity to upgrade those systems with a large margin for error. This is the goal. This is, the perspective that I see embedded in cyber-informed engineering. So let's talk about 3-2. 3-2 is risk assessment. And the strange thing about 3-2 is that one of the goals, the output of 3-2 is zones and conduits and assigning security levels to each zone, so you know how thoroughly to protect each zone. Here's the strange thing. 3-2 defines a process. It says, first you identify the system under consideration, then you do an initial assessment, then you partition the system under consideration. You ask, is the residual risk greater than the tolerable risk? And, if so, you have to provide a detailed risk assessment. None of these steps, the process, the steps are defined, but how you do it is not. How do you perform the initial risk assessment? How do you determine if risk is acceptable or not? That's not defined. This is by definition. It's because, the drafting team said, look, well, different businesses have different tolerances for risk. Small shoe factories are different from large power plants. And so everyone, a venture cap funded startup, let's just talk about business risk. A venture cap funded startup is going to take much bigger risks than a 200-year-old, utility, water utility. Why? Because the venture cap startup only has money, only has runway for 18 months. And if they can't succeed in 18 months, they go under. And so they're high risk by definition. They're willing to accept much higher risk than, a 100-year-old utility might. And so the method was not specified, just the process of the steps that you go through. Here's where cyber-informed engineering comes in. It helps give a perspective on, well, how should we make these decisions about how secure each of these zones, each of these network segments should be. And before I leave this and go to that, I wanted to point out that identifying the system under consideration, there are some very common mistakes that are made identifying, what is system under consideration? It's the OT network. You identify the OT network, that's what we're protecting with 62443. The mistake that a lot of people are making is they don't realize that sometimes our OT systems depend on IT systems for correct operation. And if the IT systems are crippled in, let's say, a ransomware attack, OT goes down, not because the ransomware hit OT, it's because the ransomware hits stuff that OT needs. Stuff in the IT network. Classic example, textbook example is Active Directory. A lot of us say, we've got regulations. The regulations say we must, if an employee leaves the company or is worse, is fired for cause, within 24 hours, we have to have all permissions revoked for that user's that person's username and password. How do you do that? You put Active Directory in, you press a button, bang, all the permissions are gone. Isn't it great? The problem is if the OT systems depend on the IT Active Directory, and the IT Active Directory is crippled in a ransomware or some other attack, we can't log into the OT systems anymore. Eventually, we've got to shut the plant down because we cannot operate it safely anymore. The automation, is no longer accessible to us. And so this is, the word here is dependencies. When we are identifying the system under consideration, it's great to draw a circle around it and say, that's OT, that's what we're going to protect. But if the goal is to keep OT running continuously and correctly, even if IT goes down, we can only achieve that goal if we understand the dependencies and if we've taken those dependencies into account in our design. So that's sort of an aside. That's not cyber-informed engineering. That's just a recent learning from using this process. The textbook example was Maersk Shipping in 2017 when NotPetya took them down, crippled their Active Directory, crippled their container tracking system. Nothing got into the ships. They still safely traveled around the world. Nothing got into the cranes in the ports. They could still unload the ships and put the containers onto the trucks. But because the IT system was crippled, nobody could print the labels that told the truck drivers where to take these containers. And so everything stopped. OT stopped, even though it was IT that was compromised. So when we're doing our sort of preliminary risk assessment, cyber-informed engineering, one of the tools in the cyber-informed engineering body of knowledge is this SecurityPHA review. This is a book that is published by the ISA. The ISA is the same people that design the IEC standards. ISC, the volunteers at the ISA create the standards. The IEC publishes them. This is 62443. So the ISA has published this book. It's talking process hazard analysis, how to use safety systems to address cyber risk as well as physical risk. And, what they do is they say, look, you're required in most places, you're required by law. In North America, it's OSHA, the Occupational Health and Safety Administration. In other countries, it's other administrations. But a lot of places, you're required by law. If you have a dangerous physical process, you have to do a safety assessment every couple of years. The output of that safety assessment is often a spreadsheet. There's a row for each unsafe outcome that we need to avoid. We need to avoid the boiler exploding. There is a column for the trigger conditions. What could cause the boiler to explode? A cyber attack could cause it to explode. An earthquake that crimps the output valve could cause it to explode. A hurricane blowing too much oxygen into the furnace could cause it to explode. And then you've got a column for mitigations saying, well, what stands between the normal operation and destruction? What tools have we got in place for protection? One of them is the mechanical overpressure relief valve. Another one is our alarm server. If the operator sees an alarm saying the pressure in the boiler is too high, the operator can turn off the furnace. Another one might be the safety instrumented system that says if the pressure in the boiler is too high, automatically turn off the furnace, turn off the power to the conveyor that sends coal dust into the furnace. And so what SPR says is you've got this tool already. You had to do it already. You're keeping it up to date. Use it, not just for safety, but for cybersecurity. And so it says, look at your trigger conditions for every outcome we need to avoid. If any of the triggers are hackable, can any of the triggers be caused, by a cyber attack? Yeah, we could send too much fuel into the furnace as a result of a cyber attack. Okay, if any of the triggers are hackable, then look at the mitigations and ask the question, are all of the mitigations hackable? And you look at them and say, well, the HMI is hackable. The safety instrumented system is software, it's hackable. But the mechanical valve is not hackable. Well, then we're good. It's not possible for a cyber attack to bring about this outcome. On to the next row. But if it turns out that a cyber attack could trigger the outcome, and all of the mitigations could be impaired by a cyber attack, then we have a problem. We have a cyber attack that could cause an unsafe and unacceptable unsafe condition. And we're going to have to put some major expensive cybersecurity, we're talking SL4 cybersecurity, into our system to deal with that threat. What's often cheaper and simpler is just to add to our mitigations, add an unhackable mitigation, an overpressure relief valve, a mechanical overspeed governor, a breakaway clutch for over torque conditions, and so on. And so this is SecurityPHA review. You use it in the preliminary assessment to take consequences off the table by small changes to the design of the physical process so that those consequences simply aren't possible anymore. And so part of the 3-2 process, if we look at our initial assessment, we say, there's still risk here. Now we have to do a detailed assessment. Again, how to do this stuff is not specified, but what you have to do is specified. First, we have to identify the threats. Then we have to identify the vulnerabilities. We have to figure out the consequences. We have to figure out how likely are these consequences to be realized by these threats, exploiting these vulnerabilities. It sounds like a lot. So let's go through this sort of one step at a time. One thing I would like to say before I move on is vulnerabilities. I do not like that word. I wish the standards, the drafting team would use a different word. The word is defined in the 62443 glossary. It's defined as any way to attack a system. Well, when I use the word vulnerability, 9 times out of 10, the person listening to me thinks I'm talking about software problems in computer products, defects that you can patch or that you can apply a security update to fix. 62443 uses the word to mean any way you can attack a system. So yes, a bug, like a buffer overflow bug that you can use to take over the system, is a vulnerability. You can patch that. But a weak password is not a software vulnerability. It's a configuration mistake. A weak rule in a firewall is not a software defect in the firewall. It's a configuration mistake. Both of them are opportunities to attack. So when you see the word vulnerabilities in the 62443 standard, don't think vulnerability. Replace it with the word opportunity. Identify attack opportunities. That's what that row means. And the goal eventually, down on the very bottom here, is figure out which security level to assign to each one of the networks in our OT system. So, security levels, what are that? Let's look at that. Oh, I'm coming to security levels in a moment. Sorry. Let's talk. So, the threats, vulnerabilities, consequences eventually determine the target security levels halfway down here. So I'm going to talk about threats first, and then consequences, and then work down into security levels and how we do this with cyber-informed engineering. So let's look at threats first. This is a sneak preview of the Waterfall threat report. It comes out in a week. April 2nd, it's due. We're madly finishing the formatting on the wretched thing. We have the data, we have the writing, we got to get it into a state that's presentable. But here is a sneak preview. The report, where to begin? The report is arguably the most cautious, the most conservative OT threat report in the world. Why? Because we count attacks, but we only count attacks that are deliberate. We don't count errors. We don't count, software defects. We don't count, equipment failures. We count deliberate cyber attacks that caused physical consequences, not attacks that stole some information, not attacks that could have caused consequences but didn't, not attacks that stole money from us but did not shut down physical. These are attacks that were deliberate attacks that shut down operations, that damaged equipment, that put people at risk. So we count deliberate attacks, physical consequences in the industries that we track. And we track building automation, manufacturing, heavy industry, and critical industrial infrastructure. And we only count the attacks if they are in the public record. No private disclosures, no confidential disclosures. So we know this report is an underestimate of what's happening in the world because we've had people come to us in confidence saying, hey, I had one of these. Here's what happened. We could not report on that. We could not count it because it was told to us in private. We only count the public data. And even though this is known to be an underreport of what's actually happening in the world, the report is alarming. How many attacks met that criteria back in 2010? We have data in the report. The appendix to the report includes the entire data set. If you want to see what attacks we counted, you can click on the links. You can go to the front page of the New York Times and see the reports for yourself. And we have data in the appendix all the way back to 2010. How many attacks were there in 2010 that met that criteria? There were one. It was Stuxnet. We've all heard of Stuxnet. 2011, there was zero. There was lots of attacks stealing information from power plants. None of them shut down any of the power plants or caused any other physical consequence. 2012, there was 2. 2013, there was 0. We bounced around between 0 and 5 for the whole decade. And then it changed. 5 in 2019, 18 in 2020, 23 the next year, 57 the next year, 68 last year. Roughly doubling every year. It's a noisy doubling, but it's roughly doubling every year. For a decade, the problem was mostly theoretical. I mean, governments were worried, forward-looking industry was worried, and then it changed. Beginning of the decade, it changed. It became a very real problem that is looking to be roughly doubling every year. Does anyone believe, with 68 attacks last year, that took down over 500 sites, impacted 500 systems, physical operations? Does anyone believe that we're ever going to see another year like 2018 where one site went down? I don't believe it. And who are these people? Most of it is ransomware. How does ransomware do what they do? They're using nation-state style attacks. What does that mean? Well, they do some phishing. They make somebody, trick someone into clicking on an attachment or trick someone into giving up their password, and they get a foothold on one machine in the IT network. And then that machine has a little bit of malware on it. The malware phones home over the internet and says, hey, boss, I got a live one. What do you want me to do? And it sits there waiting for commands. And the bad guys come in, 8 o'clock in the morning, coffee in hand. These people are professionals. Okay. They make a living hacking systems. They say, what have I got? I got 17 live ones. Let's take the first one. And they give commands to the malware. They give commands to the compromised system to look around, learn what the IT network looks like, and attack other systems. This is called pivoting. They use the compromised machine to attack other machines. Sometimes it's called lateral movement when you're attacking other machines in the same network. Sometimes it's vertical movement when you're moving through firewalls, reaching deeper and deeper into more heavily protected networks, like our IT networks. Every one of these ransomware attacks pivoted through the IT to internet firewall. These attacks routinely get through firewalls. So this is the pervasive threat. Yeah, and some of these ransomware groups are actually backed by nation states. North Korea backs their, Korea's ransomware groups to generate foreign currency for the sanctioned regime. Other ransomware groups are just so rich that they can afford to buy their own powerful nation state style attack tools. Some of them buy them from other nation states. Intelligence agencies are reporting just in the last year that ransomware groups and some of the nation states are buying and selling attack tools to and from each other. This is the world we live in. Sooner or later, ransomware is going to hit us. And when it does, the question is, how powerful is it going to be? Some of these ransomware groups are very good at what they do. Some of them are using nation state techniques. There is no longer a clear difference between nation states and ransomware. A lot of us 5 years ago might have said, oh, but I'm just a small power plant. I only produce 600 megawatts of power. Why would a nation state come after me? Ransomware is using nation state attack tools, and they come after everybody with money. Do we have money? Yes, they're going to come after us. This is the pervasive threat on the internet. This is what we need to be aware of when we're designing our security systems with 62443. The next thing is, when we're designing our security systems, we have to choose a security level. How secure do we need to be? And 62443-3 defines 4 security levels and defines them entirely in terms of the capabilities of the adversary. Now, they don't use these terms, but I will define SL1 as roughly protecting you against errors and omissions, accidental problems, or casual misoperation of the physical process. SL2 protects you against deliberate attacks. Deliberate attacks by people who don't have a lot of knowledge, who don't have a lot of money to attack you with. This is not ransomware. This is script kiddies. This is people who should know better but don't, who download a tool off the internet and press the button and go, oops, I didn't know. These are deliberate attacks, but they're not very skillful. SL3 is more skillful. SL3 in the old days was organized crime, ransomware, and hacktivists. Who are hacktivists? Hacktivists are people who have an axe to grind, a political agenda, and they don't. These people are loners. Okay, they're lone operators. They don't have an organization. They don't have money to spend developing or buying attack tools, and so some of them have some knowledge of how to attack systems. They will, download what they can off the internet and attack us with it. And they are more knowledgeable than script kiddies. They know much more than how to press a button. But again, they're not nation states. And of course, SL4 is nation states. They have nearly infinite money and talent and knowledge and resources to throw at us. SL3 and SL4 are getting muddy. They're getting blurred. One of the things that 3-3 is being rewritten for is because what the protections that used to protect us against organized crime 10 years ago were flagged as SL3 security controls. They don't do the job anymore, not against these nation state style ransomwares. And so a bunch of the protections that used to be SL4 10 years ago are being demoted into SL3. SL3 and SL4, like I said, I'm not sure how it's going to work out. It's getting blurry. Organized crime and nation states are almost the same thing. Is there really a distinction between these two anymore is the question to ask. And the other thing is that, 3-2 risk assessment says it talks about risk as a function of likelihood and consequence. If you multiply, you say consequence will be between 1 and 5. 5 is, mass casualty. 1 is, you lose $100,000. Likelihood is anywhere between very likely and not very likely. Let's say a scale of 4 or 5. You can put them into a grid, and now you can talk about risk, saying, well, if you've got a high likelihood and a truly unacceptable consequence, that's a very high risk. Here's the problem. 3-2 talks about this. This diagram is actually from NIST 800-30. 3-2 has a simpler diagram, but it's the same ideas. Here's the problem. Modern cyber attacks, the ransomware style attacks are deterministic. If ransomware hits a 1 gigawatt power plant and takes the plant down, what do? Well, we've got to go and find all the compromised equipment, isolate it, take a forensic snapshot so that the analysts can figure out how did these people get in here, restore from backup, and repeat. After 14 days, hopefully, we're back online. Imagine, however unlikely this seems, imagine that we learn absolutely nothing from that exercise, and exactly the same ransomware hits us a month later. We change nothing. If the same ransomware attack hits us a month later and we've changed nothing, it will almost certainly take us down in exactly the same way. Cyber attacks are not random. They're not, in the engineering perspective, in safety engineering, there's a mathematical model for safety engineering. That model is based on the assumption of random equipment failures. Cyber attacks are not random. They either work or they don't. If they work against a particular target, they'll probably always work against that same target. Worse, and this is something sort of an aside, when engineering people look at the problem, yes, safety engineering has some powerful tools. This is what SPR is all about, but you have to bear in mind that safety engineering is based on random failures. And so if you have 3 pressure relief valves in parallel on a boiler, and one of them fails, we assume that the other 2 are no more likely to fail. They're not more likely to fail because the first one's failed. They fail at their own rates. They're independent. This is not true of cyber defenses. If one of your cyber defenses fails and you have 3 identical cyber defenses beside it, let's say 3 firewalls in series, if the first one fails, odds are the second one's going to fail exactly the same way. These are deterministic. Cyber attackers who figure out how to break something are going to break every one of those somethings they can find. It's not independent. It's not random. Consequences. What are we talking about? When we're looking at a power plant, we're talking about gas turbines that, or steam turbines that could overtorque, that could be destroyed by manipulating a protective relay, tripping the breaker, disconnecting the turbine, disconnecting the generator from the grid for a fraction of a second, reconnecting it out of phase. And now there's so much torque, so much force on the turbine that the turbine's destroyed. There are furnaces that could overheat and blow up. There are transformers that could be overheated and burn up, that could be sent too much voltage through and impair the insulation and so on. There's all of these physical consequences. When we're doing engineering, I gave the example of a bridge. Yesterday morning, a bridge collapsed in Baltimore. 7 people died, is what it sounds like. 6 or 7 people died. A terrible accident. I was listening to an engineer on the radio half a day later explaining, what this means. And he was saying, he said, 50 years ago when the bridge was designed, if you haven't heard the news, it collapsed because a large container ship, cargo ship, lost control. They lost steering control and drifted into one of the supports for the bridge and destroyed it. And now the bridge collapsed. He said, this bridge was built 50 years ago. Today, engineering best practice, engineering sort of rules that you have to follow say that when you design a bridge, you should avoid single points of failure. You hit one of the pillars and everything collapses. And if you cannot avoid a single point of failure, if you cannot build some redundancy into the supports, then you have to consider what threats could cause the pillar to collapse, like a ship running into it, and put compensating measures in place, like a large concrete wall protecting the support, so that if a ship hits it, it's the ship that gets injured, not the support and the bridge collapsing. Engineering practice evolves over time to address these risks. The engineering practice demands robust protection for worker safety, for public safety, for environmental safety. When we look at consequences, something we often miss is equipment damage. We look at the turbines and we say, oh, someone might turn them off and the lights would go out. That's not the worst that can happen. The worst that can happen is these turbines tear themselves apart, and it takes 18 months to replace the wretched things. And we have no power for 18 months. The plant is down. This is the worst. And a big problem with these turbines is that the protection systems that are protecting the turbines from that kind of failure are software. And the bad guys know how to pivot through firewalls deeper and deeper into networks and compromise the software, the protective relays that are protecting these turbines. And so, a different way to look at the problem, the engineers look at the problem and say, we need to do something here. We can't just sit in our hands. We're expected to protect national security. National security, where did national security come from? Well, think about it. When the overpressure relief valve engages, what happens? Well, the valve opens, the steam escapes, and nobody dies. This is a good thing. And we lift the cage on the big red mushroom button and we shut down the physical process. Why? Because the last safety, we have multiple layers of safeties. We have the HMI, we have safety instrumented systems, and we have the mechanical valves. The last safety in line tripped. And we were one step away from all of us dying, anybody who was near the boiler. The last ditch safety engaged. This is never supposed to happen. When it happens, we shut the plant down and we analyze what just happened. How did it happen? Why did it happen? And what are we going to do to make sure this never happens again? This takes time. We shut the plant down. I've given this webinar twice, and I can't remember now if I'm repeating myself. So my apologies if you've heard this. We are critical infrastructure. What is the legal definition of critical infrastructure in most jurisdictions? The legal definition is critical to the nation. And so if we go down, national security is at risk. And so we don't want to go down. How can we not go down? Well, what we need to do is define engineering grade preventions for unacceptable consequences. Safety consequences we can do with electromechanical protections. If we want to prevent the plant going down at all, we have to prevent malware getting into the plant in the first place. We need engineering grade protection to prevent the propagation of cyber attacks. And this is where cyber design basis threat comes in. If probability is the wrong way to model risk for deliberate attacks, which are cyber attacks, here's another way to model it. Cyber design basis threat is a concept from physical security. It defines the most capable adversary that a security program must defeat reliably. Concrete example, we're building an embassy in a hostile nation where there might be terrorist attacks. The design basis threat document is probably classified. I've never seen one. I don't have a security clearance, but I'm told that it would contain a description. For example, something like, the security program will reliably defeat up to 3 terrorists showing up armed with submachine guns and hand grenades, trained for 3 months at this place out in the desert that everybody gets trained at. It does not necessarily need to protect against a squadron of tanks driving down the street blowing holes in buildings. That's over and above the line. But everything below the line is required to be defeated reliably. And so one of the tools that I recommend when we're using the engineering perspective of CIE and looking at 62443, instead of just saying security level 4, security level 3, put a directive together saying, we will design physical processes, our automation systems, and our networks such that no internet-based attack, doesn't matter how powerful, no internet-based attack, pivoting through intermediate networks can reach safety critical equipment or reliability critical networks or systems. That is sort of a clear directive. And now we can look at individual security controls and ask, how do they contribute to that? Where should SL4 be? Where should SL3 be? This is the heart of network engineering. This is the third book that I've written. If you're interested, there's the URL. You can ask for a free copy at the bottom. Chapter 5 in the book is network engineering. It's consequence boundaries. When we have an OT network whose worst case consequence is unacceptable, things blow up, national security is at risk because the lights went out. If we have unacceptable physical consequences, if you compromise one network, and we have another network, the IT network, where if it's compromised, what happens? Well, we get sued because we leaked our customer information into the internet. Oh, and we've got to pay someone to come in, pay through the nose to clean up the mess. It costs millions of dollars. What we have here is a connection between two networks, one of which has acceptable business consequences. You can buy insurance for all of those consequences. And the other one has unacceptable physical consequences. When we're connecting a network with dramatically different consequences at this consequence boundary, that's where we use network engineering. We don't use it between every pair of zones. It's not for every conduit. It's for the conduit at a criticality boundary. What's an example of network engineering? EPRI is the North American Electric Power Research Institute. Again, a couple hundred PhDs. They were asked a few years ago, for example, how can we do the industrial internet safely? We want to monitor our steam turbines. We got to send vibration information out to the cloud, to the vendor, so they can tell us how to manage, how to maintain these turbines efficiently. Well, the PhDs looked at the problem and said, here's how you do it. You do an engineering study on the edge devices, on the devices that are physically measuring the vibration. Prove to yourself that they are measure only, that they cannot control anything. Not that there's a software switch that they might control stuff or not. No, they're not physically able to control anything. They said connect them to your turbines and then connect them out to the IT network, or a DMZ on the IT network, or put SIM cards in these things. Some of these things, the edge devices on the industrial internet, they'll go straight out in the internet. Put them on the internet. Do not put them on your control network. Why? Well, now you can send information to the cloud, and if that information is compromised, what happens? Well, you maintain your turbine less than optimally. It costs you a couple $1 million more every couple of years. Well, that's a business consequence. Again, you can buy insurance for that. What do we avoid? We avoid somebody getting into the cloud system and loading new firmware into the edge devices. If we connect those edge devices into our control network, loading firmware into those edge devices and pivoting the attack through the edge devices into our control network, causing who knows what kind of havoc, that's what we avoid because we've physically connected them to a different network. A network with only business consequences. Don't put business critical stuff, if you can avoid it, on a safety critical or a reliability critical network. This is one example of network engineering. It's not the most common example. The most common example is the Unidirectional Gateway. Full disclosure, this is what Waterfall sells. We do unidirectional gateways. It's a combination of hardware and software. The hardware is physically able to send information in only one direction. It sends it from the power plant control network out to the enterprise network and out to the internet sometimes. The hardware cannot send anything back in the other direction. The software makes copies of servers. If we have a PI historian on the industrial network and we got an enterprise PI historian, the software will log into the plant PI, gather all the latest data, that's less than a second old, push the data through the weird one-way hardware, and on the outside, push the data into the enterprise PI so that anybody who needs the data can ask the enterprise PI for the data. It's like a unidirectional PI to PI. I mean, with a firewall, if you configure the firewall correctly, then it should not allow attacks back into the more consequential network. With this device at a consequence boundary, it does not matter how you configure it. It cannot send any attacks back into the industrial network. And all cyber sabotage attacks are information. No information flows, no attacks flow. Other examples, there's trusted platform modules that are engineering grade protection for encryption keys. There are, write once, read many storage if you need tamper-proof logging so that your security analysts can figure out, how did the bad guys get in, can find the records, and so on. One of the jobs of the Cyber-Informed Engineering Initiative, which is still ongoing, one of the jobs of the initiative is to produce an inventory of all of the different kinds of tools in all the different kinds of industries that we can use that are engineering grade, that provide engineering grade protection. What's left? Well, think about it. We have put SL4 and better. We put engineering grade protection at the criticality boundary, at the IT/OT network. The zone on the OT side that's connected to the gateway, that's connected to the network engineering device out to the IT network, that zone has really strong protection on the IT side. Does it need SL4 for the conduits to the other zones? Maybe not. It depends on what's left risk-wise. Do we need SL4 inside the zone for everything else? Maybe not. I mean, if we've got a 600 megawatt power plant, is it credible that the Russians or the Chinese are going to plant 3 spies into our workforce and pay those spies to sit in the workforce for 10 years until 10 years from now, when they want something to happen, they activate the spies and have them attack us from the inside? Is that a credible threat? For a small power plant, in most places, that's not a credible threat. For a large power plant in a small nation, for a large power plant in, that's powering, let's say, the capital city of an important nation, that level of attack might well be credible. And so we have to look at what risk is left over, and what's left over is insider risk, risks that insiders want to do ill to us, risks that insiders have been tricked into carrying malware in, risks that insiders have been blackmailed into carrying malware in. This is the residual risk. We've got to evaluate the threat and then decide how thoroughly we need to be protected and put cybersecurity mitigations in place, because as a rule for insiders, there are very few engineering grade solutions that exist for insiders. We have to use SL3 and SL4 cybersecurity mechanisms. I'm running out of time, but I want to say one more thing. I see a lot of people in industry increasingly are specifying certified devices. They only want certified 62443 certified devices in their OT networks. 4-2 is the standard that certifies. Here's the thing. As far as I know, almost all, possibly 100.0% of these certified devices are certified to SL1. What does SL1 give us? It says it gives us some accounts and passwords. The passwords might be shared between users, though. There might not be enough accounts for the users. It gives us a lock screen if we're logged in and we go inactive. It gives us the ability to back up the device. This is very basic functionality. You go, does anything out there not have this? It gives us limited security. It does not say the device has to encrypt its communications, not even when it's sending passwords around. It does not say, SL2 says you got to encrypt passwords when you're sending them across the network. SL2 says that you've got to sign your firmware so that you can't send a bunch of zeros. You can't log in with a shared password and no encryption, or steal the password on the network, log in and upload a bunch of zeros as your firmware and turn the device into a brick. It cannot boot anymore, and there's no way to change the firmware anymore. You have to throw the device out and buy a new one. These kind of protections that you kind of assume come with a secure device, they're all SL2 or higher. All you get with an SL1 is sort of basic functionality. Does it make sense to specify certified devices? It does. You want the basic functionality. Everybody wants what's in SL1. Just don't fool yourself that you've got any of the SL2 or SL3 protections when you buy an SL1 certified device. That's what I had for you. Cyber-informed engineering is coming. It gives us a way, design basis threat, directives, gives us a way to we don't need to paint the entire OT network with SL4. We don't even need to paint an entire zone with SL4. We might just have to do engineering grade protection at the criticality boundary, and in the rest of the zone do SL2 and SL3, depending on what kinds of threats are still credible against our target in this in this site. And the engineering profession has been dealing with criticality concepts, have been dealing with unacceptable consequences forever, and has been building up best practices. It's time for the engineering community to build up robust best practices to protect public safety and national security from at least the pervasive risk of nation-state grade ransomware coming across the network. That's what I had for you. I hope it made sense. I hope it's useful. Do we have any questions in the queue? Natalia, what have you got for us?
Yes, thank you, Andrew, for this informative presentation. Yes, we got a few questions. I mean, we're almost out of time, but let's take maybe a couple. So first question is, Andrew, can you give a comment on linking SIL levels IEC?
Yeah, so in my understanding, SIL is safety integrity level, and this is what's used for safety instrumented systems. Again, in terms of a safety program, there's generally at least 4 layers, sometimes 5 or 6 or 7 layers in the program. There's usually a human operator. It's usually illegal to operate dangerous, large, powerful, dangerous physical processes without human oversight. The human operator is part of the safety program. It's the operator's job, among other things. The operator has many jobs. One of the jobs is safe operation. It's the job of all of the technology that lets the operators see what's happening. All of the PLCs, all of the HMIs, all the historians, all of the alarm servers are part of the safety program because they show things to the operator who is responsible for safety. Safety instrumented systems are special purpose, whereas a PLC might be used to operate safely and operate reliably and operate efficiently. A safety instrumented system has one job, and that is prevent catastrophe. That's the only job it has. And these systems are rated in terms of their reliability. The extremely reliable ones are SIL3 or 4. I forget what the numbering system is. The less reliable ones are only SIL1, safety integrity level, because they're assuming random failure. And so the question is, how thoroughly do we have to protect the safety systems? And the answer is, it depends on the adversary. So if all we have is firewalls between the internet and the safety system, and you can pivot through one firewall after another, the bad guys can get into the safety system and mess with it, that's unacceptable. Every engineer out there will say that's unacceptable. You have to put engineering grade protection in there to prevent compromise of the safety system, unless you have electromechanical safeties after that as well. So, if the safety system is your last line of defense because you don't have an electromechanical safety, it has to work. It must be protected. You need network engineering. The most common network engineering I see on safety systems is not unidirectional gateways, it's analog signaling. You want to monitor the safety system from the HMI, run a handful of 4 to 20 milliamp loops out of the safety system into a PLC connected to the HMI. And now you can see what's going on in the safety systems, but you cannot send any messages into those systems that would attack the systems. If, on the other hand, you have network engineering in place and the bad guys simply cannot get into the OT network, now you're dealing with insiders. Is it credible that an insider is going to deliberately misoperate the safety system? If it is, you need protection in place that addresses how capable that insider is. And so the answer is, it depends. in a shoe factory where safety, systems are the only thing standing between a pivoting path to the internet and, death and dismemberment, yeah, they're going to need network engineering to prevent anybody getting into them. In a more thoroughly protected plant, they might already have the network engineering in place, and now you've got to look at what is residual. So the answer is, that's a long way of saying it depends. Sorry.
Thank you, Andrew. Another question we have, how do we use 7 foundational requirements to determine security level achieved?
I confess that I've lost track of which 7 foundational requirements you're thinking of. I have to wonder, are these the, in 3-3, you can assign a security level to a zone, or you could assign a security vector to a zone. And the vector, I think, for each of the 7 foundational requirements will assign a security level. So you could say, I need SL4 for networks. I need for data. They don't call it network protection. They call it something else, data something or other. I need, SL2 for identity and access control. Again, they call it something else. The 62443 calls these things by different names than sort of mere mortals do, and I get confused. But yeah, there's 7 kinds of protection that you can assign a separate security level to. And what this is, what I'm saying here is that if you use the engineering approach, if you use design basis threat, that gives you guidance as to how to set those levels. And it might be that you don't even need those levels, because if you say the network has to be SL4, my network integrity has to be SL4, really what you're probably saying is it has to be SL4 or better, it has to be engineering grade for the consequence boundary out to the IT network. It doesn't necessarily need to be SL4 to the next layer down of the OT network. And so the vector, applying the vector uniformly to everything in the zone might be overkill. We might be able to do a little bit, we might need to do more than 62443 asks, because the threat environment is involved, because we have these new network engineering perspectives. We might be able to do a little bit less, because once we deal with the most capable threats coming across the internet, the residual risk in many places, not all places, is lower. Some places, I'm sorry, a sleeper cell of 3 spies is a credible threat. We need SL4 across the board. It depends on the site. Again, a complicated answer. I wish I had a simpler way to say what I did. This is why I write. I do my best thinking the morning after. Send me an email and I'll try and find a more understandable way of answering that question tomorrow morning.
No worries, thank you. Let's take one more question. Is 62443 Purdue model still a valid architecture reference in security zoning?
So the Purdue model, the layered architecture that is recommended in 1-1, and that is sort of referenced throughout the rest of the standards, where you have, the internet, the IT network, a plant-wide network, or sometimes called the DMZ, the control network, the device network, the physical process, and firewalls all the way between them. That model is still widely used. It's still applicable. The reason people say, is it going away, 9 times out of 10 is because they're thinking of the industrial internet, where you've got edge devices connecting straight out to the internet with an encrypted connection through 7 layers of firewalls. And, intrusion detection is blind to this because the connection's encrypted and you can't see what's inside. It might be good stuff. It might be attacks coming back. We just don't know. That's sort of a shortcut through the Purdue model. It's not said, there's nowhere in 62443 that says you can only connect from one network to the next network up. You cannot skip networks. You cannot punch a connection through 2 and 3 layers of firewall. There's nothing that says that, to my knowledge, in the 62443 standard. But this is best practice. It's considered best practice not to punch, connections all the way through. I think Purdue still has a role to play. And what do you do about the industrial internet? Well, the OT to cloud connection is another criticality boundary. It's a consequence boundary. What's the worst that happens if you compromise the internet? Well, I'm sorry, it's mostly compromised most of the time anyway. That's an exaggeration. Banks tend not to be compromised more than a few days every couple of years. That's another criticality boundary. Network engineering techniques that I see applied, they're applied occasionally on safety instrumented systems. They're applied almost always on IT-OT interfaces, and they're applied increasingly on OT to internet interfaces. And so to me, the right way to model edge devices is either put them on their own network. Don't put them on the control network. Use the EPRI network engineering approach. Or if you're going to put them into their own network, put some network engineering in place, like, if they're on the control network, put a unidirectional gateway between the control network and the internet, or put a unidirectional gateway between the PLC network, the device network, where these edge devices are, straight out to the internet. Nothing can get back. Okay, this is how you prevent, you can send stuff out to the cloud, you can get the benefits of the cloud without anything leaking back. Now, IT may not be happy with that. They might want you to put a unidirectional gateway between the PLCs and, let's say, a DMZ that they can control, because they need to protect the information, not just the safety. The engineers are tasked with protecting safe operations. IT is tasked with protecting valuable information. We need to cooperate. So, that's another use case that we see increasingly is OT to, let's say, a DMZ, to the internet through a unidirectional gateway, through some kind of network engineering to keep the OT network safe in spite of the cloud connection, not running the cloud connection through 7 layers of Purdue and confusing what's going on with the Purdue model. That was a long answer. Sorry.
Thanks, Andrew. Well, unfortunately, we ran out of time. Any last words from your side?
I just want to say thank you to everyone listening. I encourage you to download the brain blank, my new book. I'm always looking for feedback. Sign up, get yourself sent a copy, read it, and my do I have my email here? Oh, lost it. My email is firstname.last@waterfall-security.com. Here
and we can also include it. We can also include it into a follow-up email.
Yes, please. So read the book. Give me some feedback. I rely on feedback. I try to get better. I don't make this stuff up. I don't figure this stuff out on my own. I talk to people like you who are using this stuff and, can give me feedback as to whether it's working, what still isn't working, what ideas you might have for making it work, so I can write my next book. Thank you. Thank you all. Thank you, Natalia.
Thank you, Andrew. Well, that's it for today. On behalf of Waterfall, we'd like to thank you for joining us today, and we'll see you next time.